Let's use the enhancement mode N-channel Mosfet as an example. This is the one, and this is the characteristic curve of such a transistor. First of all, as we stated before, we need a positive bias voltage called VGS. VGS means that is the voltage across the gate and the source. And we need a positive voltage here so that we can have the current flow through from this side to this side. Okay, and the right hand side is a characteristic curve. In here, we call this a threshold voltage, VTH. TH means the threshold voltage. Okay, before the VGS is greater than the threshold voltage, okay, there will be no current flow through the transistor, and we can see that the x-axis is the gate to source voltage, and the y-axis is the drain current, and this is the drain current, okay, from top to bottom. And after the VGS is greater than the threshold voltage, and the current start to rise. And we can notice that as long as the VGS is fixed, okay, as long as the VGS is fixed, then the ID is fixed. That means this one is a voltage control current source. Current source. Why we call it a voltage control current source? Because the current, the ID current, is controlled by the gate to source voltage, and once it's fixed, then the drain I have the fixed current. Okay, and there's so before the gate to source voltage is greater than the threshold voltage, and we call, because the transistor is not conductive, so we call this one as the cutoff region. So you can see this is the cutoff region. It means that there will be no current flowing through the channel of the transistor. And in this part, usually in the BJT, we call this the linear region, but here is called the saturation region. The name is quite different. Why we call it a saturation region? Because the current cannot be bigger than the current here as long as the VGS is fixed. So we call this one as a saturation region. Okay, and we also have the characteristic that in this particular solution for this curve, the VDS is 15 volts. If VDS is different, okay, it's different, then we will have a different current. We might have different current. ID may be different, only may be different. And since this is the voltage control current source, there is also a very important parameter called the GM here. Let me make this one bigger. This is a GM. GM is usually called the forward. GM is called the forward trans conductance. And the GM actually is the slope of here, is the delta ID, the delta drain current divided by the delta VGS, because so this one is ampere, right? And this one is volt. So its unit is ampere divided by volt, or sometimes or milliampere divided by volt. Okay. And because this is the ampere divided by volt, if volt divided by ampere will be the ohm, right? But if ampere divided by voltage, we call the unit is Siemens. Okay, and it usually is 1/ohm. Okay, and this GM, it acts like the HFE in the bipolar transistor, and this one control the amplification factor of the transistor. Okay, this is the basic characteristic of the enhancement mode N-channel Mosfet. And we can see an example of this one. For example, this is the such Mosfet, and it's a IRF B3004 PBF. This is the number of this one, and so we can see the drain current can be very large because it can be 340 ampere based on these conditions. Okay. And the pulse current means in the drain current in a very short period of time can reach 1,300 ampere. This is much larger than the bipolar transistor we have seen. And this definitely is the power MOSFET used in, for example, in the motor control or some application similar. And so the power dissipation can be 380 volts, 80 watts. Okay, and the maximum gate to source voltage can reach 20 ampere. This is much larger than the bipolar transistor. And we can see it's a threshold voltage. The VGS threshold voltage is 4 ampere under the condition of this one. And as we can see, it's no longer 0.7 volt. In most bipolar, most BJT, okay, we have VBE around 0.7 volt. But the VTH of a MOS, okay, can range from maybe 2 volts or 1 volt to very large one. For example, this is 4 volts. That's quite large compared to 0.75 volts. Okay, this is a typical power MOS. Okay, usually. And let's look at the characteristic curve again. Okay, more closely. Okay, if we apply a very small signal here, okay, we call this one a small signal. Maybe it's not small enough, but it's the AC signal. Okay, the characteristic curve of this one, okay, is this. The K is a constant depending on the characteristic of the MOSFET when it's manufactured. And this is VGS minus VTH to the square. Okay. In here, VGS has to be greater than the 0 for the NMOS. Okay. And after we determine the VGS, and we can determine the ID current here. So this will be our operational point, also called the Q point. And as we can see, because the MOSFET is a voltage control current source. Okay, So if the input here, okay, we have very small signal here. This one is here, and we can produce drain current, okay, something like this. And this is a drain current ID. When drain current multiplied by the RD here, if we take the output from here, and this will be our output signal here. Okay, so when ID goes bigger, then the output goes bigger. When RD goes bigger, and the VR is also bigger. Okay, and this is called the characteristic equation of the Mosfet. And let's compare the Mosfet and the bipolar junction transistor here. This is another characteristic curve. This is the first characteristic curve. But we have the other characteristic curve. Okay. And when, as we know, when VGS is determined, then ID is determined in this region. So when VGS is fixed, then ID will be fixed, right? When VGS is fixed, then ID is fixed. Then we have the current here, and then we have current here, something like this. Okay, this is although an ideal characteristic curve. Usually, it is also something like this is much close to the real situation. Okay. Okay, and the x-axis is the VDS. Okay, in here we find no matter how the VDS increase, in this region, the output current is fixed, and this is the ID current. And this part, we call this part is ohmic region. Meaning that because the VDS is small. Okay, in this region, the ID current cannot reach its originally design, and we call this one the ohmic region. And here is very much similar to the bipolar junction transistor in the saturation region. So the bipolar junction bipolar junction transistor, we call this region the saturation region. And here we can compare the ohmic region of Mosfet. Okay, and in most cases, the amplifier operate in saturation region. So the saturation region is the same as the active region or the linear region of the bipolar junction transistor. And when VGS is too small, we call this one is cutoff region. In this case, VGS, in this case, it means that VTH is equal to 0 volt. But usually, VGS cannot be, the VTH, the threshold voltage cannot be 0 volt. So usually, it will be a little bit higher than 0 volt. So we call this one, okay, is the cutoff region. This one will be the cutoff region. And this one is very similar to this one. Okay. This is the cutoff region. So this we can compare. So be careful to the term. Let me repeat again. The ohmic region here of the Mosfet is similar to the saturation region of bipolar junction transistor. The saturation region here is similar to the linear region of the active region of a bipolar junction transistor. And this will be and we also have the cutoff region here. Okay, please compare their differences. Okay, and similarly, we can have a load line here, and we can discuss it later. Okay, and if you see the reference I provide to you, we can see that we can determine the Q point by using the load line technology. But this curve has something, okay, not very correct. I especially mark it and explain it to you. Okay, and this is the characteristic curve of the Mosfet by this one. Okay, and the most important figure is the VGS. This is the VGS. So this will be the VGS. Okay. So the VGS actually is the VG. S is the VG minus VS. But as we know that the VS, this point is called VS. So VS will be equal to VG minus IS and RS. Okay, something like this. But because the IS will be equal to ID, okay, so this one can be rewrite with the VG minus ID times RS. And how can we determine ID? Okay, it depends on the other equation, meaning this equation. So these two equations are interdependent, and we need the load line here, but just be careful. This is the VG. Okay, this is the VG, and the maximum number of the ID current here, and in this particular drop, the ID should be, the VD should be here. But as we know, if the Mosfet go into the ohmic region, if the Mosfet go to the ohmic region, we can regard that the VDS will be close to 0. Okay, that means that the ID maxima here, should be VDD over RD plus RS. Okay, instead of this one, because it's no way to know what VD is unless you solve all the equations. Okay, so this is the, but when VG, okay, when VG, no, not VG here. This will be the maxima. This will be the ID here. Okay, so be careful. This is not correct. If you see the explanation, okay, in the material I provide, okay, because I copied this figure from maybe from somewhere, okay. So this will be the one, okay. But for this curve, things will be a little bit different. In this curve, we have the RS here, but in this curve we don't have the RS here. Okay, so, and this is also the log line. Okay, and this one there's only one line, and this line, and this line, they are not the same. This line is the ohmic region here. So let me draw a curve here, because this is our Q point. So the actual characteristic equation is something like this. Okay, this is similar to the curve here. Okay, and this line divide the entire plane to the ohmic region, and this part are saturation region. Okay, they are different. Okay, and therefore we can use the load line here. This is the load line, so this is the VDD here, and the maxima of the ID will be VDD divided by ID. But if we have the RD here, or RS here, then this part, okay, just as I said before, should be VDD divided by RS plus RD. Okay, this is what we need to be careful. This is not the one that is explained by the left-hand side figure. Okay, so be careful. There's RS or not. Okay, I will just show you an example later by solving the Q point, and so that you can just know how to calculate the operational point of the N channel Mosfet later.